So now we can start. Yeah.
Okay, so let me continue. So I want to do several things today. So first of all, I wanted to talk. The main thing I want to talk about is this. So I want to give you a third or second proof of the fact that this m-dimensional bundles, non-commutative bundles with flat connection, let's say on the surface, are the same thing as, to be precise, birational isomorphic to one-dimensional local systems on the corresponding bipartite graph. And the second thing is I want to explain what is the Poisson nature behind the story. And so I probably start with the first. And so this, I mean, the proof that we discussed last time, it's very easy and clear, but still it's a little mysterious because it leaves the question, what's the role of those bipartite graphs and why they work and what's going on. And so I'm going to present a different approach to this, but this needs some detour to some general notions. So I want to talk about something which we called admissible digit sheaves. But as I said, the goal is to give another proof. I can consider them on manifold. Let's start with a manifold. But actually, let's do it on a surface. So let's just suppose we have a surface. You can do a manifold, but I'm not going to use it. So the idea is that we want to interpret our moduli spaces as moduli spaces of something, of this admissible digit sheaves, and then they have greater flexibility, and using this flexibility, the cluster structure will be basically obvious. Okay, so what are those admissible digit sheaves on the surface? So we have on the surface some collection of lines, and these lines later will be coming from bipartite graph, but in general we have some collection of lines. I assume that these lines in generic positions. This means that they intersect like that. And then I wanted to ideally to consider something like complex constructible complexes of sheaves on this surface with singular support given by the zero section and cotangent bundles to this curves, but this is actually not sufficient to do what we want to do, and so I need to consider this DG sheaves. So let me explain the definition, and you will see why it works a little later. So first of all, we give yourself a co-oriented collection of these hypersurfaces. So the co-orientation, there's one direction here is chosen like that. It's a co-orientation, so some kind of something like that. Yes. A question? No. Let's say that this H is a collection of co-oriented smooth, in general hypersurfaces, but in outstation curves on an oriented surface. It's called S, and a generic position, as explained. Now, instead of giving you definition, what is a category of digit sheaves? It's an enhancement, DG enhancement of the category of constructible sheaves on the cell complex. Let me give you just some economic model for this. And so if you want it, I'll give you the definition after this. So it's a kind of proposition definition. So you can use this as a definition for now, but it's actually a proposition. So what we can do, we can consider the dual cubical complex. So we can put, it's actually the dual complex. We can put a vertex on each face of what we had before. Then we consider segments which connect these faces. So we do the dual cubical complexes, red picture like that. Okay. And so I called K cubical. And then the claim or the definition is that an H is this collection supported DG sheaf is described by the following simple data. So the data is the following. So you have a complex called CV dot. Actually, sorry, it's not a complex. It's a graded vector space, no differential yet. For each vertex. V of this red cubical complex. And then this is one piece of the data, and the second piece of the data is this, that there is a map. Let's call this map delta K. Okay, who is K? So I have to let me call it actually F. I have to take a face. So face of this cubical complex. In our situation, we can have a face given like that. Only you can have a two-dimensional face. In general, you can have cubes of high dimensions. So this is our face F, either this or that. And so I have a map which goes from the complex which sits in the bottom left vertex here. This is this vertex, V minus of this F, to the one which sits on the top right, V plus of F. So we have such a map. And this map actually shifts degree by 1 minus K, where K is dimension of this face. In our case, 1 or 2. Okay. So we do this for each, as I said, K-dimensional face F of this cubical complex. Now we put condition. The condition is that for every face F of our cubical complex, we want to consider, sorry, the word complex is kind of overused. Now I consider complex in the sense of homological algebra. I want to consider complex related to this face, which is just given by the direct sum of all these graded spaces which sits in our vertices, and this dv is distance from our vertex. Oh, sorry. It will show up in a second. Just sorry. Okay. It's distance from vertex V, which we take to the bottom left vertex, V minus of F. And so on the picture, which I was drawing, we have 4 graded spaces sitting here, here, and here, and here. And this is going to be in our complex in degree 0. This is going to be in degree 1. And this is going to be in degree 2. So we have 4 graded spaces sitting as the 4 vertices. So that's this space. And it also has a map. So let's call this map D sub K. Will be differential. Is by definition the signed sum of maps delta, which we had above. So here we had this maps delta f, and so we take sine sum of this maps delta f, and so we get a differential. So on this picture, this means that we have differentials which go like that, and like that, and like that, and like that. And most importantly for us, we have a differential which goes this way. And this one, I mean, we have a map which goes this way, and we put all of them together to make this map dk. And now we require that, first of all, dk square is 0. And if this is the case, we say that we have this DG shift. So that's a notion of a DG shift. So I don't know, are there any questions? Should I explain more on what's going on, or I just can leave it as a formal definition? Maybe I can explain the idea which behind this. So we want to talk about DG category of constructible shifts. And let's suppose that you have something like cell complex. And so you want to put some complex here. You also want to put some complex here, and you want to put some complex here. And then we want, in the usual situation, we have restrictions. You have a map of complexes from here to here, from here to here, and also from here to here. But usually we say that the composition of the first two equals to this third. But in our case, we say that if you take this composition this way and this way, it's actually only homotopic to the one which we have here. So the composition of 1 and 2 is homotopic to 3. And we actually give ourselves this homotopy. And then if we have more dimensions, then we put homotopies on the homotopies and so on and so far. All this, it's very easy to give a definition as just some functor from certain A infinity functor from certain A infinity category related to the cell complex to the category of complexes, still the DG category. But all in all, in our situation, this boils down to what I said, that we have natural restrictions map and some compositions, actually composition of two of them, these ones will be homotopic to the third one. Now, if you take the cell decomposition, the original one, and consider the dual cubical decomposition, then one can express this data in terms of this red cubical thing. Just as I said, so this, I mean, I can explain how to do this, but you can consider this a little exercise. But the point is that we put complexes everywhere, like this point, this point, this point, and this point. Then we have these natural maps, but we also have homotopy which go in this way. Now, what's the role of the co-orientations? We actually assume that if you start, that the microlocal support of what you get supposed to go in the cotangent direction given by this co-orientation. This means that if you restrict from here to here, it's isomorphism. And so I can kind of skip this data. And so what stands here as a morph to what stands here, as a morph to what stands here, the only data is how you go from here to here. That's the only data of the complex you have. And also here, that's how we go from here to here. But then the compositions this way and this way, they're not equal, they're homotopic, but their homotopy is given to us explicitly. Okay, that's the end of the definition. So are there any questions? Is there any need to elaborate on this, or you can just leave with this? So what do you feel?
Sorry, probably I didn't understand how vertices V minus and V plus are defined. They're defined canonically, or?
Yes, yes, yes. Whenever you have a cube, whenever you have a cube, there is the leftmost vertex, which is bottom leftmost, and there is this upper, the most upper vertex. The cube.
What is the lowest and the highest? I mean, on two-face.
On two-face. So if you have a two-face.
No. On surface, there is no canonical top and bottom on surface.
No. So remember that it's a very good question. So I skip something. So that's why you Didn't understand. Remember that we have co-oriented lines, co-oriented. This means that if you consider, for example, this square, you know that this vertex is distinguished and this vertex is distinguished, because here the co-orientation goes towards this vertex and here it goes out of this vertex.
Okay.
So the notion of bottom left and top right is fixed by the data of co-orientation. I'm sorry I skipped this and it was indeed unclear. Thank you. More questions? I'm not sure what this silence means. So is that completely clear? I actually, you don't have any questions, so it's completely unclear. No, please,
Well, rather completely unclear, but maybe let's see what follows.
It's not going to be more clear. That's the end of that's essentially the end of the definition. So if it's unclear, you may ask something, but you may use this as a, I don't know, as a black box. Okay, let me give you the key. First of all, so I give you a definition of this DG sheaf. And so what is the role of this complex? So we have this complex, this one, which corresponds to the face. So this complex calculates something. Actually, what it calculates microlocal support. If you consider, two lines, and they're co-oriented this way, up and to the right, then you can ask for the microlocal support in those directions, like in this direction, this and this. This is the only directions where it is unclear what this microlocal support is, and the claim is that the microlocal support at these directions is calculated by the cohomology of this complex which I just introduced. And so it's a statement. And now I wanted to put a condition. So the condition is that the actually this complex has no cohomology. So the condition is that the cohomology, this complex, this one, is acyclic. But let me say this in a more elaborate form. So I can even erase this for now. So here is the key definition. We say that an H supported DG sheaf is admissible if the following conditions hold. So it's more than just an acyclicity. So it's the conditions is that the complexes CK with differential decay, CF, I call them F, for each phase. Satisfy the following conditions. And first of all, if you consider a situation when the dimension of this phase is 0, which means it's a vertex, then this complex can be concentrated in 2 degrees. And these degrees are actually 0 and 1. So unless cohomology degree P is 0 or 1, I insist that the cohomology of this complex is 0. So once again, so we're sitting on the surface, and if you take here some generic point, this complex could be in 2 degrees, in degree 0 or in degree 1. Now, if you take now point which sits on a line, which means the dimension, this is f, dimension of your is 1, then the complex can sit in only 1 degree. And this degree is 1. So here the cohomology can be in degree 1. Here, sorry, in degree 0. Here it could be only in degree 0. Here it could be in degree 0 and 1, 0 and 1, 0 and 1. And if you consider any higher dimension strata, which means that the dimension of f is bigger, in our case, it just means equal to 2, but it's a generic condition, then this complex is just a cyclic. And so the last condition, this is the one which guarantees conditions of microlocal support. The second condition, which tells you that the cone of this map from here to here is concentrated in 1 degree, and this is actually microlocal support on this line. And in generically, we can have two components of these complexes. So this is the main definition. It's a very strange definition. So we were very surprised when they somehow faced this definition. And its main property is the following, that the category of this admissible, or I would say H admissible DG shifts is invariant under certain moves, under the following elementary moves.
Sash, excuse me, the word microlocal, it means something?
Oh, yes. So it's a general fact, which I skipped, that if you have a complex of constructible sheaves, of course, it has support, but it also has a microlocal support. This means that if you have a point, then there are some directions where a complex has support and some directions doesn't have support. So for example, if you have a line and you take your complex, it sits here, and you restrict this complex to some neighborhood, for example, here, to the bottom. It may happen that this map is a quasi-isomorphism. Then it does not have support in this direction. But when I say that it has microlocal support is in direction up, so I draw it like that. When I draw this picture, this means that when you look down, it's quasi-isomorphism. When you look up, it's not. And so you have to take the cone. But what happens if you sit in this neighborhood, and what happens if you move a little bit up? So you have to take these two open sets, and you have to restrict from, let's say, this green, no, not green, from this one to the intersection. You can have it by this color. And so when you restrict from here to here, you have a map of complexes because you have complex sitting here and complex sitting here. And you have to take cone. And this cone is what you put on this vector. If you want to consider what happens on the vector which looks downstairs, you do the same, but you shift your neighborhood downstairs a little bit. Use the same procedure. So that's a general procedure. Whenever you have a hyperplane in your tangent space, if you want to calculate microlocal support in the conormal direction, you take some a little subset here, and then you move it slightly in the direction you consider, something like that. And then you restrict to the intersection of this two subsets. So you take the cone of the mat from this brownish to the blackish restriction, and this cone is the singular support in that direction. Okay, Boris?
Okay, thank you. Yeah.
And so we want to model category of constructible sheaves, but actually the category of the usual derived category of constructible sheaves is not adequate for the task, as you will see in a few minutes. And so we need some DG version of this category. But what we want to have complexes which have microlocal support. In our collection, of lines, and actually only in the direction which was specified. So it has microlocal support in one direction, non-trivial, but it's trivial in the other direction. And then we end up with this definition of DG sheaf, which is supposed to describe general constructible complexes. And then to put these conditions which you want to consider, we introduce this complex for each cell, and so it's responsible for the calculation of this conormal support. And then we put some extra condition, these ones, which are very strange. Again, this is a very strange condition, and we don't really know why this condition appears, but they appear. So there is some kind of conditions which there's some kind of subcategory which has very remarkable properties. And so these properties I'm going to discuss. Is that clear or remotely clear now? I need some feedback. I can't proceed talking to.
Clear what? Sorry.
I give a definition. This is definition of an admissible DG sheaf. And I try to explain that what this definition means. This definition means that we're talking about DG enhancement of constructible complexes which have certain properties, and their properties is that at generic points they're sitting in degrees 0 and 1, they're cohomology in degrees 0 and 1. And this on these lines, so if you look at these complexes, then you have, where is that? You have those maps here. If you take cone of any of this map, like this one, or this one, or this one, or this one, you will see your micro-local support sitting here, 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 and here. And we postulate that these micro-local supports are not a complex, but just sits in degree 0. And then if you take the total cohomology of this complex, then we say it must be 0. This means that there are no micro-local support out of the in the sitting at just in this point. Okay.
Well, okay. It's more or less clear. After that, we try to follow you and see what is going.
Okay. So now the definition.
You can give an example of some classical sheaf that gives rise to this data.
No, definitely, but let's do this later. Okay, this is part of the story, but I'll do this a little later. So for now, the point is that we have such a strange subcategory, and it has some interesting properties. So this was my explanations, but the point is that this category is invariant under certain elementary moves. So who are those elementary moves? So that's a theorem. Let me write it again. That the theorem is that we have invariance with respect to the following elementary moves. So we can take two lines which intersect like that, and we can assume that they're co-oriented like this. And then we can move them through. This means this co-orientation just means that we're talking about some conormal bundle, Lagrangian subvariety, and the condition is that we can move them through and nothing happens. So this is 1, this is 2, and so this becomes 2, this becomes 1, and the co-orientation will be, of course, like that. So it's like that and like this. So the claim is that if you consider such a move, then there is canonical equivalence between these two DG categories, okay? And in particular, this implies that there is canonical equivalence between the stacks of objects. So that's move number 1. You can actually do it in an opposite way. So you can take, for opposite co-orientation, you can take the same picture, but you can co-orient it inside here and also inside here. And then when you move them through, you see what you get. So you get this kind of co-orientation. But what you cannot do, you cannot make them intersect. So if you have this picture and this is oriented this way, co-oriented this way, this is certainly not the same as what you would get if you move them through. So it's different. This is forbidden. So this is can do that. Okay, this is now a type 1 of elementary move, and then there is a type 2 elementary move. If you have a triangle, if you have two lines, and the third one is trying to move through, then you can do this. The statement is that you can do this. You can move it this way. And you can do this for whatever orientation you can imagine here. So I'll draw you some of them. For example, you can orient this way, and this way. And when you move, of course, these orientations stay the same. So it's picture like that. And there are some other ways to draw orientation. So all of them are okay. So this reminds, of course, the well-known theorem by Lerm, Kashivara, and Shapira, which says that if you consider the category, this is called GKS theorem, that if you consider the derived category of constructible sheaves on a manifold, that's invariant in the same sense that you have equivalences under any Hamiltonian isotopes of microlocal supports. But this is not what we're talking about here. So this is a great theorem and of course an inspiration, but this theorem is not applicable in this situation because we are talking not about we are talking about not all derived category, but we're talking about first of all DG category, and second we put some very strange conditions in this category. So it's not at all clear why anything should be preserved because of the strange condition. And secondly, our category is not invariant under arbitrary moves of Legendrians. It's certainly not invariant, so we don't consider the situation what happens if you have a cusp and so on. And there are moves under which it's not invariant. So for example, if you pass through the cusp, things breaks down and so on and so forth. There are only this kind of moves. And the category is different and I would say smaller. So that's the main upshot. Is that okay? All right, now, having said this, I can give you one-line proof of the theorem which we had before. So it's another proof of, I call theorem X, which lives at that point on the surface. So this is a theorem about equivalence, flat connections, m-dimensional flat connections, and one-dimensional flat connections on a bipartite graph. So here is the observation. So first of all, what kind of bipartite graphs we consider on surfaces? Actually, sorry, before I go to that, let me first of all give you a little more information about bipartite graphs before I go to the proof. So given any bipartite graph, bipartite ribbon graph, gamma. So this means that we have vertices of two kinds. So there is the notion of zigzag passes. So we assign to this collection of zigzag passes, or just call them zigzags. So who they are? So what we can do, we can, when we go along the graph, we decided to turn to the right when you see a white vertex and to the left when you see a black vertex. So if I want to draw a more complicated picture, so you have something like that. And then you have whatever may happen here, or any number of edges can grow here. But then when you move on this bipartite graph, what you do, you turn left at black, right at white, left and black, right at white, black, and so on. So this is zigzag path. Actually, you don't even need bipartite structure, because what you do, you alternate your direction of move every time. So if you move left at this vertex, you have to move right here, and so on so far. Okay, is that clear?
Yes.
Yes, good. So the next point is that actually these zigzag passes are oriented if you have bipartite graph. So you can decide that they are oriented from white to black, for example. But if you have an edge, we always have two zigzag passes, because again, you can go left here, right here, and so on. And these are the orientations. So they oriented this way. Okay. And the orientations are canonical. This means that if you have your graph gamma, then you have collection of co-oriented or just oriented, the surface is oriented, the same thing, of oriented passes. So they're sometimes loops, sometimes just arcs. So they're oriented passes. And these are the ones which are going to be carry the support of our DigiChiefs in future. So when we talk about bipartite graph, what we do, we consider zigzag passes and then forget about bipartite graphs at all. It turns out that we can reconstruct bipartite graphs from this net of zigzag passes, which satisfies some very mild condition. But let me skip this point. So basically, I'm saying that zigzag passes with little condition is the same thing as bipartite graphs. And so from now on, instead of talking about bipartite graphs, I usually talk about zigzag passes. So that's how the two stories are related. Now I can ask a question. What kind of zigzags we want to consider on surfaces which are relevant to our problem. And let's do an example. So let's draw once again this picture which we were drawing before this, a natural bipartite graph which is related to the triangle. So remember that it looks like that. Something like that. And now let's draw the bipartite graphs here. So let's do this, for example, starting here, and it goes like that. Oh no. Oh, sorry, you can stop for a second when you're doing this. Sorry. So this is how the zigzag passes looks, some of them, 3 of them. But you can consider the other, and they will look as follows. And then you have another 3, and they will look as follows. So then you go like that. Okay, there are no other zigzags in this picture. So there's 3 kinds of zigzags, and they look this way. Now, if we just forget about bipartite graph, so what we notice that we have a triangle, and then if you just consider one type of them, for example, this purple, then you can homotop them and see that they go like that. So they go around one of the vertices, and the green ones, they go around the other vertex. If you just consider just green ones, and just blue ones, they go around the third vertex. So this means that this kind of intertangled collection on the left, you can isotop all them and get this clean collection which go around the vertices on the right. But here, but they are very different collections. If you consider bipartite graph, So here they come from a bipartite graph. Here they do not come from any bipartite graph. You just isotoped all of them here. And so if you consider now more complicated situation, for example, if you glue surface from triangles like that, then immediately see that these zigzags, which we actually consider, has the following property. So if you draw a surface and consider the punctures on the surface, which you have, this is your punctures, then around every puncture, there will be precisely m zigzags which go around every puncture, if you're talking about m across 3 case. So you'll see pictures like that. So they're isotopic to this collection of passes. And so I noticed this long ago and make a definition. I said that a bipartite GLM graph is such that is such that its zigzags can be isotoped to a picture like that, where the condition is that whenever you have any puncture, there will be precisely m, where m is GLM, it will be precisely m zigzags. You can isotope them to precisely m zigzags which go around this puncture, and every zigzag know its puncture. So for every zigzag there is one and only one puncture to which it can be isotoped. So I call this ideal bipartite graphs, so GLM bipartite graphs, already introduced notion. So this is a paper I wanted to give you a reference for that. This is, you can find this in 1607, 05-28. Okay, so now then when we prove main results about cluster structure on surfaces, what we really use, we use all bipartite graphs whose zigzag has this property. And then when we were talking about action of the mapping class group, remember I was saying that when the mapping class group X, what you really need to understand, you need to understand how the flip works. And they really take one bipartite graphs to a very different one. But it turns out that there are intermediate GLM graphs which you can put in between them, such that the transition from one to the other will be going by 2x2 moves. So once again, the point is that these GLM graphs are flexible enough to do whatever you want to do on a surface using just these 2x2 moves. But then these conditions, it's some strange conditions. So what does it mean? Okay, so now I'm relating the story to the previous story about microlocal shifts. The point is the following: that if you look, remember that our admissible DG shifts, they're invariant under moves. And actually, the moves which we use to move from this picture to this one is admissible one, because when we move, we have only this triangles, you know, triple crossings on the way and nothing else. We just move this pink, sorry, red or whatever. Here, the blue ones here, and the red ones here, and so get this configuration. This means that the category which assigned to this collection and the category which assigned to this collection are the same categories. But now let's try to understand what are these categories by their original definition. And then if you look at this picture, you will see that the corresponding category, in this category, you just get collections of
Stash, I will explain that on your picture, you have blue, green, and red, and they are lines, and you consider the category which is corresponding to them or not?
Absolutely. Thank you, Boria. I maybe didn't say this.
So on the left and on the right, what you are doing?
On the right, it's the same thing. So I have this purple, blue, and green lines. They live on a triangle. This also lives on the triangle, but their configuration is very different. But they are related by these moves which we allow. You can homotop or isotope this collection, which intertangles in a complicated way, to this one, which is very simple, using the elementary moves which I just explained, using actually elementary moves of second kind. You don't need the first kind. This triangle moves, okay?
But then in your picture of genus 2 curve, all your circles are purple for some reason. Should they be green and blue also, or what?
Yes, they can be green and blue. I don't have enough colors to mark. I mean, in this case, if you...
I should imagine them to be green and blue also, yeah?
No, all colors are not important, what you say.
Colors are absolutely not important. It's just for pleasure of viewing them. But what is important that you have this collection of zigzags, and the condition on the graphs which you consider on surfaces is the following: that whatever collection you have, every zigzag knows exactly one puncture around which it's going. So, for example, look, if you try to, let me give you one more example. If you try to do this bipartite graphs, which corresponds to triangle with a puncture. Okay, so this is your puncture. And then, as you see from the previous picture, you will have this kind of, you can homotope it like that, this homotopes like that, and this homotopes like that. So altogether, you're getting 3 circles which go going around this puncture. That's what you see from those 2 pictures immediately, right? Misha.
Yes, thank you.
I'll say yes. Okay, and that explains how you get those pictures on surfaces. So you just take ideal triangle. A way to do this is to take ideal triangulation, put these pictures inside of ideal triangulation, then draw these zigzags, and then you'll see this picture. Okay, then you can isotope it to this picture.
Yes, thank you.
Okay, now let's ask the question. So if you consider our zigzags realized in this concentric way, what will be our category of admissible digit sheaves? Or even a simple example here, what is the category of admissible digit sheaves which lives on a triangle? It could be any surface, for example, triangle, and has this microlocal supports, has this curves. Now, I also will put conditions that our digit sheaves, it's an extra condition, that it's 0 near the vertices. Now, if you think about this, if you have such a picture, so you have some surface, you have sheaf which is 0 here, and then you have a co-oriented line like that. And so when you cross it, the only thing which can happen is that you get some vector space sitting here. Because remember, my condition was that you have something sitting 0 and 1 here, something sitting 0 and 1 here, but when you take the cone, it's supposed to sit in degree 0. If you start here from degree 0, you cannot put anything in degree 1 here. You must put it in degree 0, and it must be an embedding. But in this case, it's obviously embedding. Then if you take the next line, then again, it's co-oriented this way outside. Again, this means that when you cross it, you get a bigger, so this vector space V1, you get bigger vector space V2, and they're nested. This is in this one. When you take the next, if you have it zigzag, and again, it's co-oriented the same way. So you get a short subspace here, V3. And so this means that around each vertex, we have a filtration, which means a flag. That's the data. It's precisely the data. Now, if I put the conditions that my microlocal supports has dimension 1 everywhere, then I have a complete flag. I can put a different condition, but I decided to just make it one-dimensional. And then in this picture just shows that you see just 3 flags. That's it. So configurations of arbitrary sleeve flags is the same thing as this microlocal digit sheaves, which has 0 at the vertices, and which have microlocal support, which is one-dimensional. It's just one-to-one correspondence is bijection. Okay? Is this clear?
Yes.
Yes. Okay. So
sorry, I have a question here, Sasha. So
yes.
On your left graph, there might be some like generic conditions for your flags, I guess. On the right graph, there is no conditions.
On the right, there is no conditions. Exactly. Linkvi, we will, so it's a very good point. So thank you for making this point. And we will come exactly to this in a second. That's exactly the point, that on the left-hand side, we got precisely this stack of configurations of 3 flags in m-dimensional vector space. No genericity condition, nothing. It's all configuration of three flags. It's a stack. So we get some kind of stack which this picture provides us. Okay. On the left-hand side, however, and in the original problem, in the construction of cluster coordinate system, we deal not with all flags, but we deal with some the risky open part. And now I'm claiming that that's exactly what you can see from the left picture. And here's why. So when we see a left picture, then you usually see that near crossing of the zigzags, I make them black now, that's a crossing point. So zigzags are co-oriented. So let's do it this way. And then we can have whatever complexes in degree 1 and 2 sitting here, 0 and 1 sitting here and here. But I want to put a condition that the complex here is 0. It's a condition. And I want to put conditions as 0 here. So again, remember that when we have a crossing, this kind of 4 domains are completely canonical because they're specified by the co-orientation of those lines. And so we put conditions as 0 here and 0 here, and then there is nothing left but just to see that this is C and this is in degree 1 and this is C, because there is no other admissible DG shifts in this situation which have one-dimensional support and 0 here and 0 here. All right. But now I said this is DG shift indeed. So we have this 0, C sitting in degree -1, C 0, and we have a maps, but of course there are only one map to 0 and from 0. So those arrows are given to us and they're trivial. So they're trivial arrows. But in our data, we have one more arrow. We have homotopy, this one. And this is something which is absent in the usual language of constructible shifts. You can't talk about homotopy, so it's not part of the data. It's like a condition, but not a data. But here we have a homotopy, and this is homotopy between two 0 maps, because this map equals to 0, and this map equals to 0. But the homotopy between them is an isomorphism, White's isomorphism, because the complex must have no cohomology. This was the main condition. So this must be an isomorphism, and it has to be given to us. It's part of the data. So we end up here with the following observations that when we have picture on the left, near each crossing point of the zigzags, which corresponds to edges of my graph, you have such a standard situation. But now if you think about this, how bipartite graphs looks in general. So it have white vertex, black vertex, it looks like that. And so now it has a zigzag passes. So let's draw them again. And also has actually shouldn't really use different colors here too much. So there is also this this ones. So now I was talking about what's happening near this point, but the same thing happens here and here. And if you look at all these co-orientations, you will see that they're co-oriented like that. So it's co-oriented this way. It's co-oriented this way, and so on. So it's co-oriented this way. And oh, no. This is actually, I think I made a mistake here. It's going this way. So the bottom line is that this black vertices corresponds to these domains which are co-oriented inside. White vertices correspond to domains which are oriented outside. And then we have mixed domains which are oriented neither inside altogether or outside. They kind of alternate. So we call them mixed domains. And so our DG shift is 0 on mixed domains by definition, as we just discussed. But then it has something which sits here in degree -1 and something which sits here. And then there is a map between them. And so that's exactly the local system data. So all in all, we got local system on a bipartite graph because we have for each two vertices, white and black, we have an arrow between them. This is our homotopy. And so we conclude that's a conclusion. That the data of an admissible DG sheaf are related to the XAF of bipartite graph is a plus condition 0 on mixed domains, that all the DG sheaves are just 0. This is equivalent to saying that we have a flat bundle, an actual line bundle, if you put conditions that could support as one-dimensional on the bipartite graph. So, but I don't have to say this, that's line bundle. So just any line, any vector bundle with connection on a graph is the same thing as a admissible DG sheaf plus the condition is 0 on mixed domains. Okay? Is that clear, or at least statement clear?
Plausible. We have thinking.
Huh?
What? It is plausible. Yes.
Okay. No. I proved this because I just explained that if you have a crossing, so this is a crossing, and here's a crossing appears here. If you have a crossing, if you insist that on this domain which mixed and on this domain which mixed, you have zeros, then you have no other choices but to put vector spaces of the same dimension on this domain which is white and on this domain which is black, and relate them by an isomorphism, because that's a homotopy between 0 map and 0 map.
Yeah,
so you have no, you have no other choices. Yeah,
and you
so
also
now,
impose an auxiliary condition that they're all one-dimensional. Yeah.
Yes, that's so we can say they're one-dimensional at the end of the day, but that's not that important. Let's do this. But what is important that this condition is an open condition. Because whenever you have a complex and you put conditions that two neighboring cohomology groups are zeros, it's an open condition. For example, if you have a map from vector space to a different vector space, if you say this map is an isomorphism, it's an open condition. But now we put conditions that they actually zero everywhere. So again, it's an open condition, and just special case of what I was saying before. And therefore, we get some open, the risky open part in the moduli space of all DG sheaves. And that's it, because now if you return to the picture we're talking about, so as Link he asked what's the role of those conditions on the left. They give you something open, which embeds to our stack. And what you see here, this open part are precisely flatline bundles on this bipartite graph. I just explained that that's what DG sheaf condition means in this case, admissible DG sheaves. And on the right-hand side, the admissibility means that you just have 3 flags. And the easy theorem that this elementary moves preserve this category just means that you have that one sits inside of the other, and because it's open conditions, that's the risky open part. So we are done. We constructed the cluster chart because we already discussed that this is local systems on bipartite graphs. This is a like non-commutative cluster chart. So if your local system is non-commutative, so we took configuration of 3 flags, maybe non-commutative flags, and using this bipartite graph, construct inside an open torus. And if you consider a surface, we do the same thing. We consider any GLM graph on this surface, and it provides you an open path which parameterize DG sheaves which are 0 mixed domains. But for different bipartite graphs, there are different open parts, and so that's a cluster. This is a cluster chart. And so now this theorem, which I stated originally, that at least we have birational isomorphism of this moduli space of bundles with flat connections with local system on graphs. So it becomes totally obvious, and assuming that we get this picture with admissible DG sheaves, it's one-line proofs. But what is more important is that it actually explains what's going on, because it explains why we consider this kind of bipartite graphs. The answer is we consider them because the zigzag passes are isotopic to the standard ones, And if you consider this kind of standard ones, they give you precisely what I call framed local systems. So this gives precisely what we called with Volodya for framed m-dimensional local systems on S. But the word framed means that you have this invariant flags. And that's exactly what this data gives you. So all this this data gives you one flag, this gives you another flag, this gives you a third flag. And what you see inside gives you the local system. So it kind of explains why cluster coordinates exist on framed local systems, but they do not exist on local systems. Because actually, this data of zigzag passes is kind of the most important part of the data. And if you just dealing with local systems, you just don't have it. Okay, so that was one of the punchlines, and I just want to make sure that you got at least something from this discussion. So are there any questions, or should I explain something or repeat something?
Sorry, I have another question here. So for each temperature, there are 3 cycles. So
Yes.
I was wondering if you can exchange the positions of those 3 cycles. And does that correspond to some like well group actions associated to temperatures?
Lifi, you're asking a very good question. And so let me, so first of all, I cannot for free exchange them because this is non-admissible move because they're co-oriented the same way. So you're right that there exists symmetric group action. It's not that easy. I mean, in a sense, it corresponds to this, but I cannot, at the moment, I have no means just to explain this as simple, but you're right that this is the essence of the matter, but we don't allow this moves at the moment. Okay, it's a very good question.
Thank you.
More questions, or I don't know. No questions. All right. So then I can explain the story about the Stokes data because it fits very natural to this framework. So if you have no questions, so let me go to Stokes data. But basically the point is that with Stokes data, what happens is the same. Last call for questions. Is there anything you want me to say here? Or?
Could you comment on elementary moves a little bit more?
Yeah, and what do you want me to say?
Like why they appear here at all? I mean, I'm sorry, but I don't understand. Like, what happens with the surface?
No, with the surface, nothing happens. You have surface, on the surface, you have zigzag passes. And I'm saying that zigzag passes, they're, of course, Legendrian or Lagrangian submanifold or Legendrian links of this three-dimensional contact manifold associated with the surface. And ideally, we want to move this Legendrians freely if you consider all constructible sheaves. But in our situation, it's very strange because there is this very strange conditions that we put here, that not that we have sheaves, they are complexes generically, not that we have any complexes, they are very, very specific conditions on their cohomology. And so, and nevertheless, this seems to be a very important object because when you look at some examples of these configurations of hypersurfaces, they deliver exactly the Moduli spaces you want to study. And then when you try to deform this kind of net of lines, they deliver you the cluster structure if you can deform them in this admissible way. And if you ask me why I mean, I don't have any more comments on that, except that it still looks to us very mysterious why such objects exist, and we don't know any reason why it should exist, but somehow it exists. It's like if you ask why, it's like perverse sheaf. It's not exactly a sheaf and has some strange condition, but it has some nice properties. So it's also, it's not all complex contractible sheaves, just some of them. They're not sheaves, but they have this nice microlocal properties, but not all of them, but some of them. I guess that's all I can say about this. So we prove that there are equivalences. The proof is easy, but I don't have more comments on this.
Okay, thank you.
Mhm. All right, so let me go to local Stokes data. So Stokes data. So my goal is to explain that the same thing happens with moduli space of Stokes data, that they describe it using the same language. Namely, basically what I'm going to say is that if you have a surface and if you have some special points, punctures on the surface, that instead of drawing these concentric circles, you can draw some other curves which going around, but they intersect, something like that. And then drawing these curves, you can still consider, this picture is not completely adequate, so there are 3 of them, so that maybe this way. So you consider these pictures, but you better consider, if you want to get geometry to Stokes data, you better make them, all of them intersect. So you have to do it like that. So going like, you can do something like that, and then you have 1, 2, 1 more. So you can consider any pictures like that. So what I was trying to achieve that when you go along the array, you hit 3 of them, so that it hits the same number. When you go outside, and then any of 2 of them intersect. So you can draw any pictures like that, and then you can consider, so you can assign to this moduli spaces of admissible DG sheaves related to those pictures. And this is the modular space of Stokes data, stacks of Stokes data. They are part of the story. So they just smoothly embed as a part of this more general story. And so if I just specify what kind of curves I should consider here, then I get one of the definitions, and I get literally the definition of the modular space of Stokes data. But then if I manage to deform in such a way that they intertangle in a bipartite graph, I get cluster structure. And the claim is that you can always do this when you talk about modular space of Stokes data, and that's why it has a cluster structure, that's why it has non-commutative cluster structure, because it fits in this framework. But But to implement this, I have to give you some definitions. So let's do that. So what is a local Stokes data? So you consider a collection L of smooth oriented loops. Let's call them L1 and so on, LM, on punctured disk. And then you specify the ones which you want to consider. So you want to consider such collections, and we can call them ideal, if the following conditions holds. First of all, if you consider any 2 of them, where I is not equal to J, then this intersection is transversal. So it goes like that. And second condition, that each loop Li rotates to the right. This means that you go this way, but you absolutely cannot go this way, because here you turn left, so you shouldn't do this. So that's forbidden. Okay, so we can call this, in this case, that L is an ideal Legendrian link, because you can put this to the projectivized tangent bundle to your surface. I mean, sphericalized, I would say, tangent bundle to your surface. And actually, it's very easy to see that this is the same thing, that L is the same thing as an element of cyclic envelope of braid group, of positive braid group. So we can consider semi-group positive braids, and we take a simply cyclic envelope. So it's the same data, because what you do, you consider curves like that, and they go around. And so if you just consider from the center, you'll see that you're talking about this kind of braid. I draw you a braid if you go around this point.
And what is the cyclic envelope?
What?
What is the meaning of words cyclic envelope?
Oh, I mean, if you have a collection of generators like S1, S2, S3, S1, S2, you can kind of put this on a circle. A formal definition, Misha, is that you consider the operation of cyclic shift, which move this generator to the right, and then take coinvariance of this. But what it really means, so what is this S1? So this is a simple transposition which you draw like that. Then what is this S2? This means that you have another one which goes like that. And so if you keep doing this, you draw in a braid, right? So this braid, you imagine that you have some kind of annulus on which this braid is, in which you draw this braid. But then this braid, not necessarily, if it just ends, then you have an element of the braid group. But then it can go around any way you like. And then this object, you can call it formally cyclic braid, but actually what it is just this picture.
I see.
Okay.
Thank you.
And it rotates, and it rotates to the right. So I don't want to consider situations here when you kind of do things. When, as I said, when you do things like that. So that's their eyes talk, but I don't want to consider them. So they just turn to the right. Okay, so that's a simple combinatorial reformulation. What is a braid? And then the definition, the second definition is that we say that this L is of Stokes type. If
Sasha, but
yes.
braid, when you're saying who is going up or down.
Yes, exactly. But here you have a plane. Good, specific way. So you have a plane, and you first of all, what you do, you can consider the corresponding Legendrian links. This means that you consider the tangents to those guys, and then they live already in three-dimensional space. You can think about it this way. But also, when you go around, like you say, okay, if they go this way, then you decide which one is over each one. For example, you can say that this one, if you cross this way, this one is over this one. It's your decision, but you can do it this way, and then it's well defined. Because we turn to the right all the way, so every time we have a crossing, this goes over that. Okay.
Okay. Okay, fine.
Okay, but thank you. So now, important thing. So we say that L is of Stokes type if the following conditions actually specify that the intersection of them is not empty for any I which is not equal to j, that all of them intersect. For example, the one which we had in the beginning, these concentric circles, they are not of Stokes type. This is not Stokes. It's important, but not Stokes. Okay, now what is the local Stokes data? That's the definition 3. Local Stokes data is the following thing. So first of all, you have a local system. V on the circle of rays. So this is just punctured tangent space to R2 modular. I mean, homotopically, this is tangent space to R2 minus 0. Then we have an increase in filtration. F everywhere except finitely many rays. Some rays R1 and so on, Rn, which sits on our circle. And so the picture is like that. So you have this rays where things may break up a little bit. And then you have on this circle, you have filtration, which exists everywhere, but on those directions. So here something happens, this filtration. So we already have filtration on the complement to them. So so we have filtration everywhere except those rays, but at those rays we have a certain condition, namely if you consider the filtration, the east part of the filtration, which is on the left of some vertex Ri, this is the same as filtration on the right of this R. If you're talking about east part of this filtration, this is true for almost all I, when I is not equal to certain A, some integer. And for those, for this A, there is another condition, that the associate gradient of length 2 of the flag, which I define as just Fa plus 1 divided by A minus 1. It's actually direct sum of two lines from the right of weight A and from the left of degree A. So there is a condition.
And the A is just some A.
Some A, yes. So for some A, so there is A. This A tells you what happens at this crossing. So you usually have some collection of lines which go around, and this is the lines number 3 and 4, and so this is like transposition sigma 3, 4 in the previous discussion. But it tells you about the A. So here is A is 3 because they distinguished as 3 and 4. So it's A n plus 1. So A equals 3 and A plus 1 is 4. Okay. So that's the condition. And so once again, so you have, if you imagine that you have this picture with a braid, something like that, then you have filtration, which is everywhere. But at this moment, here, something happens with your filtration, because here what you see to the right and what you see to the left, they don't go continuously to each other. They jump, and how they jump, I just explained. And now you realize, so this is a notion of a local Stokes data. And so now you immediately realize that this is the same thing, that Moduli space of local Stokes data is the same thing as a Moduli space of admissible DG sheaves, the actual sheaves in this case, near this puncture P, related to L. So we have to specify some L here, plus condition, so which satisfies the condition that there's 0 near P. And this is pretty much trivial statement. So because all it says that whenever we have this kind of crossing, so we have some vector space here V0, then it embeds the vector space here V1 and V2. So we have these embeddings, and then they sit in certain V1, 2 here. And then if you look at the definitions, the definition of admissibility, it's just equivalent to this condition which we have here. So I say it's basically tautology. So it's just like the statement that the flag is flags are moduli space of admissible DG shifts vanishing at zero. It's basically tautology which follow from the definition in one line. But it's important observation that moduli space of, now if you have a surface where we have a global situation, where we have several punctures, and out in each puncture, as I explained, we have some data of Stokes type, then we can talk about moduli space of Stokes data on a surface. It's just either you repeat this definition locally, or you just say it's moduli space of admissible DG shifts which vanish in the punctures. Okay, so that's a linear algebra part of the story. But then there is, of course, differential equation part of the story. So, so the next thing is we want to get local Stokes data from differential equations. And so for this, I need to remind you some classical facts about differential equations. This is called formal classification of irregular D models, or irregular singularities of differential equations. And it goes like that. So I need to remind you that we have notion of Poisson series. So what is a Poisson series? It's a Laurent series in some fractional power of your local coordinate. So D is an integer. And then we have a field of Poisson, all of Poisson series. And so what this field is, this is just algebraic closure of the field of Laurent series in your variable Z. And inside of this, you have the integral closure of Taylor series, which you can denote this way. So this is by definition integral closure of Taylor series, formal series. And then you have important object. You want to consider quotient of the field of all Poisson series by the ones which are regular, or you say this integral closure. Use the wrong. Actually, I can do this. Okay. This guy. And in concrete terms, you do the following. You consider all Laurent series in Z of 1 over D, and you divide for those which are actually Taylor series in Z1 over D, and then you take union of all D. So that's this important object. And now definition, so we call that G is just the Galois orbits, and Galois in this case is isomorphic to group Z hat orbits on this quotient. Let's call this quotient star on star. So basically I consider this quotient, but actually only Galois orbits matter. And so in coordinates, you can write this Poisson series in any concrete case as sum of lambda k Z2 minus k divided by D, and the sum over integers. And this lambda k's, they are any complex numbers. And then we declare that this f of z is equivalent to the guy which sits on this Galois orbit, which is just exponent of 2 pi I divided by z multiplied by z. So that's the Galois orbits. And finally, we have a projection from the formal disk, punctured disk to formal punctured disk, which corresponds to D to 1 cover. So this Z is W to D. D's W's is precisely the Z over 1 over D, which we were talking about before. So we have this map. And now the classification comes as follows. It's a classical theorem, first half of previous century. So we take holonomic T model on spec C of W generated by exponent of this Poisson series. So this is one thing which we take. Then another thing which we take a local system. Let's call this V on this W plane on spec C of W. And this is topologically just a circle. And then we consider the push forward with respect to this map of the tensor product of E to F of Z, tensor product with this local system. And so the claim is that any irreducible object is obtained this way. This means that, so this is a classification. So in simple terms, it means the following, that if you want to write down just one equation, all you do, you say that you want to consider something like exponent of logarithm W raised to some power K multiplied by exponent of this Poisson series. And you want to consider functions like that. You can take any linear combination, of course, of these logarithms. And so all functions like that, they are the supply of functions which you consider. So what's important of this function f, it's only a singular term. So it's actually a polynomial it's actually Poisson polynomial. In Z to minus 1 over D. And then the differential equations they satisfy, that's your differential equation. Now, the theorem is that the category of holonomic D models on spec C of Z is equivalent to the direct sum of blocks given by those D models. And so this means that any of them is a direct sum of this D G of E to F G of W tensor. Okay, so that's a classical theorem. Now, how this classical theorem applied? So if you have a differential equation with a regular singularity, that's the second part. So we take a flat connection, let's call it in some vector bundle on analytic puncture disk. And then we know that if you restrict to the formal puncture disk, then you have direct sum, which we have here. And then they come with a collection of this Poisson polynomials, which you can just write as sum of lambda j k z to minus k divided by dj. All right. So that's the key players. Now, what we do, we restrict this formal power series as a function to a small circle of radius epsilon, where epsilon is a positive small but given number. So we call the circle S1 epsilon. And then we get collection of curves. So who are those curves? So you just write down these curves, which depend on the angles theta, as follows. This is the radial part multiplied by the phase, and the radial part is just, and that's the key formula for us, it's exponent of a real part of this Puiseux polynomial restricted to this circle. So that's the key thing which you want to do. And so when you draw this, you will get exactly the curves I was drawing around here. So all these kind of curves, they appear when you draw, when you just draw this zj equals, when you take some Puiseux polynomial and draw these curves for concrete epsilon, you get curves like that. So when epsilon moves slightly, so it deform, but when epsilon is getting sufficiently small, the picture you get does not depend on epsilon, so it stabilizes. And so that's basically it. So this is, so from this, you get your Legendrian L, which corresponds to this differential equation locally. And then you just apply the previous story. So you say that you consider the category which related to this collection of Legendrian links on the surface, and this is your category of moduli space of Stokes data. And in order to prove that it has cluster structure, following the proof which I gave you today, all you need to do, you need just to show that you can deform them to a bipartite graph. And the statement, yes, then you can do it. And actually, it's not that mysterious that you can do it, because the main part of the story is that you can do it on triangle, and you can do it on a kind of bigone. And then if you put this together, so you can just cut your surface on pieces, deform these collections of Legendrian links to bipartite graph, and this gives you the cluster structure. It also gives you Poisson structure, although I didn't discuss this yet, although I have to finish, I think. So this is how we get cluster structure in the situation when all this singular supports are one-dimensional. Because remember, we have this, where is it? We have the local system. And this local system, it describes this kind of term. And this local system in general is multidimensional. And so in general, we would not get cluster structure just from here. So what we need to do this usual trick. So we need to refine this local system VW by a complete filtration. And then geometrically, this means the following, that instead of drawing this kind of link, we draw kind of a twin link. So we just, if it's three-dimensional, then introducing filtration is the same thing as drawing well, let's suppose if it's two-dimensional, just two links like that. If it's three-dimensional, then I have to draw one more. So I'm afraid the picture will be more complicated, but it's very easy. If I would have a circle, then all I'm doing just writing collection of concentric circles. And if the circle is actually entangled as a Legendrian link, you do absolutely the same. And so that's what somehow did the job for local systems, and the same trick does the job for moduli space of Stokes data. So you get some kind of cover, which is generically finite cover. It's finite cover, it's a Galois cover with product of symmetric groups, which tell you the dimension of how many satellite links you draw here. Then the action of this group is cluster, and therefore, if you you get cluster structure on this covering, and this is enough to quantize the original modular space of Stokes data. And so with all these remarks, in the end of the day, we can quantize any modular space of Stokes data. So that's the story about Stokes data. So I finished the story. The only thing which I didn't tell you about Poisson structure, this non-commutative Poisson structure on bipartite graphs. But before I go there, so when I was talking about this non-commutative modular space of Stokes data, you see all this discussion can be repeated for local systems of vector bundles over any ring. Nothing changes because basically all you do this little linear algebra, this little isotopes, and this you can do this over every ring. And so the resulting object is this modular space of non-commutative Stokes data I was talking about before. Now, this is the end of this story. So is there any questions?
Sorry, may I ask? So I wanted to ask maybe a side question about the situation, maybe even without Stokes data. So if you just have some punctures, so if I understand correctly, usually you consider a situation where monodromies around these punctures are in a general position. And my question is, what happens when this monodromies become special? For example, they have n-1 coinciding eigenvalues or something like that. Is there any description of the same kind in such a situation?
So the description I gave you, that's the point. It describes all Stokes data. It doesn't matter which way they're generic, not generic, eigenvalues coincide, not coincide, and so on. So it doesn't really matter here. So when you say that eigenvalues coincide, all that happens is that you have terms in solution like that. So you have a Jordan block. So when you have a Jordan block in your local system, this means that your eigenvalues coincide. And so coincidence of eigenvalues in this language means that this local system, this is local system on a surface, on a circle. So this is just a linear map in a vector space. And so it's just a statement that this linear map has a Jordan block. It's okay. So just become multi-dimensional local system. So it is completely okay. And so the story doesn't change, but you just have like three-dimensional support sitting here. The local system on the circle is three-dimensional.
But there are situations where there is no Jordan block, there is just a diagonal matrix with coinciding eigenvalues.
If it's diagonal matrix, it's just direct sum of one-dimensional local systems. So operator can be Jordan block, can be just diagonal. It doesn't matter.
But it's in one point, but then we can glue it with all other points, and this will not be a direct sum anymore.
No. So this description locally gives you a Legendrian link. So it gives a Legendrian link, and it also you have to consider on the loops of this Legendrian links arbitrary local system. This is a local description. If you have 2 points, different points, you have local description here, you have local description here, they don't talk to each other. So local descriptions, it doesn't matter. So they of course all sit in the same local system, but for the description I give it plays no role. It's a complete description. So because of this classical theorem, you get complete description of all kind of topological types of data which you can get. And then for each of them, you have the corresponding modular space of this of Stokes data or DG shifts. It's the same thing. And this is the stack we are talking about.
Okay, thanks.
I want to just say once again that the key point in all this story, which we were discussing today, was that we consider, the key point is that we have cluster structure. So this moduli space of Stokes data is a classical object, but the key point is that it has a cluster structure, and we have this cluster structure because it has bipartite graphs assigned to it, to this local description, and because we have this kind of notion of this admissible DG shifts, which include in their definitions homotopes, and this homotopes actually describes the cluster structure. So to describe the cluster structure, there's two things which were important, that we have bipartite graphs, and then we talking about moduli space not of constructible sheaves or complex of constructible sheaves, but we're talking about moduli space, which is a DG object, therefore it has homotopy built in, and this homotopy becomes the only visible thing when you go to bipartite graphs. It gives this local system. This local system is built from these homotopes.
Sorry, probably I didn't understand in a right way these things with Puzo series, but can you provide an examples for example, GO1 or GO2 case, some classification of possible arrangement of lines?
Sorry, which lines?
Curves. I mean, these curves which define a Gendron link.
No, but you take any polynomial in fractional negative fractional powers of z, and you just draw this curve. So I'm not sure what else.
For example, for GL1 case.
For GL1 case, it's in this case dB will be 1. So draw this curves. Not.
Yeah, I just didn't understand how to draw these curves.
I can show you the place where it's drawn.
Okay, please.
So there is this formula. Sorry, line doesn't. Anyway, there is this formula which tells you that all you need to do. So, okay, so once again, so you have a circle. This circle is on the distance epsilon from 0. Then you have your Laurent series given this way. It's actually a Laurent polynomial because only negative powers of z are important. There are finitely many of them. Positives are not important for the considerations, not needed for the considerations. And then you write down this series, and then you take what you do then on each line. You draw the real parts of. It's a multivariate function, but still you draw the real parts of it. And then when you rotate the line, so these real parts, they somehow they make this collection of curves, so they kind of entangle in a certain way, and that's what it is. I'm not sure what else I can say, but it depends on the curve what you get. So, for example, if you have something like sum over some matrices divided by z square, where matrices is constant, then what's important is the eigenvalues of this matrix, and then what you get some kind of circles. So you can do this as an exercise, but you get collection of circles which all will intersect. But you just draw write down solution in this form as this Laurent series, and just consider what happens with real parts. You get some trigonometric polynomials, and you have to plot them. I don't know.
And this is a formal solution to.
Yes. So if you give any Puzo series, it produces some kind of curve, and then there is a moduli space of Stokes data which corresponds to deformation class of these curves. So topology of this curve determines a component in the moduli space of all data.
And FJ, sir, I'm trying to understand. FJ are they're vector valued or they're number valued?
No, FJ. If you put the index j, then they are of course functions. So they're functions. They take real part of functions. But the index j shows that we have a vector valued function here.
Okay.
So once again, the point, informally, the point is that whenever you solve differential equation in formal Lorentz Puiseux series, you always get solution like that. So you can get something like W to lambda multiplied by some Puiseux series of W. So this W to lambda tells you the local system. It's a local system on a circle which has monodromy calculated from this lambda. And this is a Puiseux series. And this is not important when you're doing this topological type. You ignore this completely at the first moment. Then you use this Puiseux series in order to draw the curves. And then you remember now about this W to lambda because it tells you what kind of local system you put on this curve.
Okay. Thank you.
Now, an interesting thing happens here because there is this huge wild mapping class group. So why it appears? Because if you consider, you can now deform the coefficients of those series and see what happens. So when you deform these complex numbers, your curves start moving, and they are moving in a way you can consider only admissible moves, which are moves which we describe where only triangle can change and all things like that. And so because of that, when this Legendre-Linz moves and then when come back, you can decompose this as a sequence of these elementary transformations, and then you get a cluster automorphism of your Poisson variety because of the theorem which we were talking about before, basically. Because you get all these equivalences which result in some cluster automorphisms. And that's how this wild mapping class group appears in the story. Any other questions?
No, thank you. Maybe it is too long and we have to think about this.
Okay. Actually, let me make one more comment. So, okay, so this kind of the story ended. I just want to make one more comment about bipartite graphs. So just 1 minute, okay? So,
okay.
So if you have any this moduli space of Stokes data, then we assign to this collection of bipartite graphs. And then it produces this cluster structure. But bipartite graphs actually produces much more than that, because what is a bipartite graph? It's a picture like that. Okay, and then you can consider the dual graph. And so the dual graph, it's a picture like that. So it has vertices and it has edges. And the edges actually, okay, so there are edges, but a priori they are not oriented. So you get some kind of graph like that. And so this way you can say that you have a quiver. This is just a red quiver. So you have vertices and the edges. But you also have not only quiver, you also have a potential. What is a potential? Potential is any cyclic word on this quiver, but by definition. But in this case, whenever you have any black vertex, you have a loop in your quiver which is going around this vertex. And you can say that it's going around, it's not exactly a realistic picture because we have to have, no, it is realistic. So it's going around clockwise. And if you have a white vertex, you have to declare that it's going counterclockwise. And so this is, so our potential is just the sum of these loops around black vertices and around white vertices. So they're oriented in a different way. But now if you have potential, let's denote this by W, then there is an object which is called Ginzburg TGA, related to this quiver, which comes from bipartite graph, and potential, which comes from bipartite graph. And Ginzburg TGA, it produces 3D Calabi-Yau category. And then you prove that if you consider a 2x2 move, something like that, I mean, I defined 2x2 moves before. So if you consider 2x2 move, then this 3D Calabi-Yau category to one graph and 3D Calabi category to second graph, you get canonical functor between them. And so now this story bipartite graphs, it gives you that you have collection of Calabi-Yau categories and functors between them, which satisfy some natural conditions. And in the end of the day, they're like local system. It's like representation of some extension of the wild mapping class group, but of course not the representation. It's kind of local systems of this Calabi-Yau categories on the classifying space of this mapping class group. And so you can ask question, so what is the role of this local system of Calabi-Yau categories in geometry? And conjectural answer that it describes the Fukaya category of certain open Calabi-Yau threefold, which naturally corresponds to the original Moduli space. And actually this is, now it's even a theorem in the case when you're talking about SL2 and a surface. This was established by Bridgeland and Smith, but in general, it's a conjecture which you can find for surfaces in that paper I was telling you, 16th, it's my paper. And the same should be true for arbitrary Moduli space of Stokes data. So the bottom line is that this combinatorial construction using bipartite graphs, it gives you actually several things, which like it gives you cluster structure. It also gives you this explicitly described Calabi-Yau three-dimensional categories. And so it seems that it's just somehow intrinsically important object which relates to this Moduli space. So that's the only comment which I wanted to add to the story. Okay.
Okay. Thank you very much, Sasha.
Thank you.
Thank you.
Yeah.
Thank you.
So, so then we resume to tomorrow on 3:30 Moscow time, and maybe one more announcement. I guess everybody already knows that on Friday we have 2 additional lectures by Misha Bernstein and Bore Fagin on toroidal algebras and extensions of Gelfand-Zetlin basis business to this situation. Okay.
And the, okay, yeah. The lectures are recorded, right?
Yeah.
Even on Friday.
It's,
Okay. Okay.
okay.
Mhm.
Stop.